Good morning, everybody. Welcome to the High Energy Density Center's Seminar Series. Pleased to have with us today Dr. Snejana Arbazi, who is a professor and chair of applied mathematics at the University of Western Australia. Before that, she worked at Carnegie Mellon University, the University of Chicago, Stanford University, and SUNY Stony Brook in the United States, and at the Osaka University in Japan, and the University of Bayreuth in Germany. She got her PhD at the Landau Institute for Theoretical Physics of the Russian Academy of Sciences, and she is a citizen of the United States. Dr. Arbazi is a theoretical physicist and applied mathematician, specializing in the dynamics of fluids and plasmas and their applications in nature and technology. Her key results are the mechanism of interface stabilization, the special self-similar class and the interfacial mixing, and the fundamentals of Rayleigh-Taylor instabilities. Her key contributions to the community are the program Turbulent, Mixing, and Beyond, and the editorial work. Her achievements are recognized nationally and internationally by the National Science Foundation and National Academy of Sciences in the United States, Japan Society for Promotion of Science in Japan, and the Alexander von Humboldt Foundation in Germany. She was elected Fellow of the American Physical Society for deep and abiding work on the Rayleigh-Taylor and related instabilities and for sustained leadership in that community. And she serves on the APS Committee on Scientific Publications. So this talk is an unclassified talk, and please be aware of any export control issues since people are logged on from all over. If you have questions and you're in the audience here, please wait until I pass you the microphone. And if you're online, please enter your questions in the chat field and I will read them after the talk. Otherwise, please sit back and enjoy. Thank you.
Thank you so much for inviting me, and I would like to express my deep gratitude to Frank Graziani, to Paul Grabowski, to Bruce Remington for making things happen, as well as to Jessica Carlton, who organized all the technical logistics, and to Lawrence Livermore National Laboratory, particularly Physical Sciences Division, for supporting this visit. And to National Science Foundation, actually, who supported a part of these results, as well as to the University of Western Australia and Australian Research Council. I would like to express my deep gratitude to the colleagues, Dave Arnett, Bruce Remington, and Dr. Srinivasan, as well as to the late Evgeny Meshkov, and to the students for being encouraging on, developing all this theory of fluid instabilities and interfacial mixing and the applications in high energy density plasmas. I would like to emphasize the role of the graduate students who were involved in this project, including the students from University of Chicago, from Carnegie Mellon University, from University of Western Australia, and to give some references, because essentially this sort of approach, what we will be discussing today, fluid instabilities are interfacial mixing, I call it a group theory-based approach. And a group theory-based approach, and it allows actually a treatment, unified treatment, I would say rigorous treatment of a broad class of processes to which fluid instabilities and controlled by fluid instabilities and interfacial mixing. Since I have been already introduced, I keep this slide, and I also skip a discussion about what is the difference between mathematics, science, and engineering, as well as it was discussed actually on the Monday talk. Do I speak loud enough, or I should speak louder? Good? Okay. So we will be discussing today Rayleigh-Taylor instabilities and Richtmeier-Meshkov instabilities and RTRM interfacial mixing, especially in applications in the high energy density plasmas. And their dynamic control a broad range of processes in nature and technology at astrophysical scales and at molecular scales, starting from core collapse supernova, thermonuclear flashes on the surface of compact stars, photo evaporated clouds. And it's a very famous reason for a delimiting factor in inertial confinement fusion. It also plays an important role in magneto-inertial fusion, as well as in the Z-pinches, and in nanofabrication, including light material interaction, material transformation under impact. RTI and RMI, or Rayleigh-Taylor and Richtmeier-Meshkov instabilities, develop whenever fluids of different density are accelerated against their density gradient. And classical RTI is for constant acceleration, and classical RMI is for impulsive acceleration, which is in experiments is induced by a steady shock. However, with time, Rayleigh-Taylor or Richtmeier-Meshkov interfacial mixing develops, and this process, mixing process, is believed to be self-similar. In high energy density plasmas environments, and actually in general in realistic applications, accelerations are usually variable. They are not constant, they are neither constant nor impulsive, they're actually somewhere in between. And this work is focusing on impulsive acceleration. So I will have a lot of materials. I may be processing a little bit quicker and skipping some slides as needed. However, indeed, there is a lot of information, but I would like to present actually sort of a cohesive, nice picture, which will be coming from the point of view of, general theoretical physics perspectives. The main results that I would like to outline in advance would be the following: that reality RTRM mixing with variable acceleration belongs to a special self-similar class. In this self-similar class, self-similar Rayleigh-Taylor or Richtmeier-Meshkov dynamic may vary very broadly from superballistics to subdiffusion, yet depending on the acceleration, yet with all these rich dynamic properties, in any of these subregimes, Rayleigh-Taylor and Richtmeier mixing, interfacial mixing keeps memory of deterministic conditions and in general has a dynamics prescribed by the deterministic conditions. We show that the properties of RTRM mixing depart from those of similar Kolmogorov turbulence, and they also depart from those that are prescribed by similar blast waves, including Taylor-Sedov and Landau-Guderian-Stanikovic solutions. So it's a classical Rayleigh-Taylor instability, and we see that, what it is. It's when there is a heavy fluid like water on the top and light fluid like water on the bottom, and we have an atmospheric pressure which is 10 to the 5th power pascals. And from the estimate of hydrostatic pressure, we see that the water column 10 meters in height, that atmospheric pressure should be sufficient to support a water column 10 meters in height. However, when we take a glass of water, put it upside down, we see how flow from it over on top, and this is a Rayleigh-Taylor instability. The reason why it occurs because this interface, this state of equilibrium between the heavy and light fluid water, or raw heavy and raw light, is an unstable state. It's an absolutely unstable state, and the interface is transformed such that the small perturbations start to grow, a structure of bubbles and spikes appear, and bubbles are the portion of the light fluid which penetrates the heavy fluid. The spikes are the portion of the heavy fluid penetrating the light fluid. There is a shear at this interface. Vertical structures develop, forming a mushroom-shaped cup, and we have our transition to self-similar mixing. In classical Richtmeier-Meshkov instability, acceleration is driven by a shock wave or when it is impulsive. In fact, actually, one should be very cautious when we say it, because actually in shock-driven acceleration, the shock wave not only introduces impulsive acceleration, but also it leaves some vorticity behind the shock as a result of interaction with an interface. And the initial growth rate set, it depends actually on a number of factors. So it's a classical Rayleigh-Taylor. Taylor experiment that were conducted in 2 tubes ranging from about 2 meters in height and about 10 centimeters in diameters. And the system were water air as well as ethanol air, and the rising bubble velocity was about 30 centimeters per second. This is actually one of the first applications of Rayleigh-Taylor instability, which probably is very well known in this audience. So I would like to return to the figure which I have been discussing on Monday, but I do like it very much because it very well illustrates the difference between the diffusive mixing as well as the interfacial mixing. Because what this figure presents is the development of the instability from an initial stage when there is a heavy fluid marked in red and light fluid marked in blue. As time progresses, we see that the interface between these 2 species becomes corrugated, and the green color essentially marks the interfacial particles. However, if we will zoom it in, and zoom it in and zoom it in, we will see that this mixing and this mixing are not the same quantities. And I would like to emphasize that these huge values of the acceleration, which is approximately 10 to the power 10 of the Earth's gravity, are typical for molecular dynamic simulations, which is actually also corresponds to high energy density regimes. So why is the fluid instability and interfacial mixing are important in high energy density plasmas? Usually I give on the talks a lot of examples, but I would like just to illustrate maybe some few. And this would be again for instance, dynamics of photo-operated clouds, which describing the process of the formation of a burst of a star when inside this tower the interstellar gas is dense enough to collapse under its own weight. And astrophysicists believe that these small droplets, which may be seen here and here, they are the places where the young stars start to born. Supernova is a central problem in astrophysics, and data from supernova remnants are believed to encapsulate information on the processes of the entire stellar evolution and nuclear synthesis. And this will be essentially the type 1a supernova, where it is believed that Rayleigh-Taylor type of mixing dominates the propagation of nuclear flame front and provide conditions for synthesis of intermediate and iron peak elements, whereas here in core collapse supernova, we may also synthesize heavy mass elements. There is actually maybe not as high energy density conditions as in supernova, but still pretty actually dramatic conditions they associated with the connection in stellar interiors and in the sun. This may be one of the first experiments from Lockheed Martin Solar Astrophysical Laboratory here at Stanford, actually made in 2003, when the weather in the sun has started to be diagnosed. And this is one of the maybe massive numerical simulations done maybe 15 years, some 10 years ago, of the solar convection in the NASA simulations. The reason why I'm showing this picture is that because people do observe a lot of convective cells on the surface of the sun, and they would like to predict this, the weather, actually, the appearance of the electromagnetic storms, at least with some reasonable degree of predictability. But they also notice that the convection at the surface in the solar interior is dominated by the so-called downdrafts. It's a portion of the material that is actually being synced into the interior of the sun, and these downdrafts, they do behave like Rayleigh-Taylor mixing. Fusion plasmas, I'd better not describe it in this audience because, it was my first time on Monday when I saw this pellet, and actually I just would like to mention that here in the picture it's blue, but in reality it's red. So, but it's still very nice, very tiny target, which is about just 2 nanometers in diameter. And when we look at our maybe very first numerical simulations in spherical geometry done, I don't know how many years ago, but nearly 30 years ago, and more recent numerical simulations, we still see that this actually problem is extremely challenging to tackle by numerical methods, including the CFDs. Nanofabrication and material processing is another important application of the fluid instabilities, and this is molecular dynamics of about 4 million Lennard-Jones atoms of the melting of the material under the impact of a strong shock, and MD simulations, as well as the particle methods like smooth particle hydrodynamics, including 10 to the power 5, 10 to the power 6 particles in Richtmeier-Meshkova instability in the in the convergent geometry, as well as in the planar geometry. Here I would like to show the picture about MD simulations and Lennard-Jones liquids showing the interfacial vertical structures, because this is actually was a situation when a shock was progressing from the side of a capsule to inside and then going back. So the green color moves the direction of the motion of the particles. The interface perturbation have been imposed. So the green color moves the particles that move to the center, and red, they are moving from the center. So we have a shear at the interface. Here, the shear is the side of the structure of the bubbles and spikes. And if we will be looking at the velocity field here, what we see that a lot of baroclinic velocity production, actually a lot of vertical structures produced at the interface, but not in the bulk. And the molecular dynamic simulations here, even though they're somewhat ancient in a sense, but they do give us a nice picture, actually presenting that the vertical structures may be formed even at the level of approximately 100 atoms. So what is known and what is not quite known about Rayleigh-Taylor instabilities? Traditionally, in case of constant acceleration, it is believed that instability progresses through 3 regimes. Linear regime, when there is an exponential growth of small amplitude perturbation, then to the nonlinear regime, when the amplitude grows linearly with time, and then self-similar regime, when in case of constant acceleration, the growth is quadratic with time. This formula actually tells us why the phenomenon is so challenging to study, because characteristic length scale depends on the square root on the wavelength lambda of initial perturbation, and the smaller the lambda, the faster the instability grows. There is when we have a characteristic viscous scale, for instance, characteristic viscosity set, for instance, by kinematic viscosity nu, there is also the characteristic length scale, and I would like to point your attention that this length scale, according to our analysis, keeps an important role, keeps actually a cutoff role up to the very late stages of instability, including mixing, self-similar mixing regime. Even though traditionally it's believed not so, but I am going to prove that it will be so. We have a structure of bubbles and spikes that is being formed into the nonlinear regime. And if we will be looking at the self-similar mixing regime, Rayleigh-Taylor flow characterized by large-scale structures, small-scale structures, and energy transfer to large and small scales. The theoretical problem, it includes the conservation of mass, momentum, and energy, and the equation of state. The problem is a 3-dimensional space and time. Our E large is energy density, and W is an enthalpy. We presume that our acceleration is variable, and we also may augment our equation with a viscous term, for instance, in the momentum equation, which is prescribed here. If this equation would be as simple, and we would consider it like constant density situation, forget about the energy equation, then it would be the millennium problem, Navier-Stokes equation. But we have something more complicated here, because we need to solve boundary value problem at a freely evolving interface, which is described by the function theta, whose value is 0 at the interface and positive or negative in each of the fluids. But it comes with a separate subset of partial differential equations describing the boundary conditions at the interface, plus there are the boundary conditions at the outside boundary of the domain, and boundary conditions set by the initial conditions defining symmetries and scales. It looks like that. So if you would like to, for instance, apply a Heaviside function, describe one subdomain of fields, and the Heaviside function in the other fluid subdomain of fields, we may actually derive boundary conditions, and these would be the conditions the following. So we'll have a normal component of velocity and pressure continuous at the interface, and tangential component and enthalpy being discontinuous at the interface. Boundary conditions are here at the outside boundaries of the domain, and these conditions mean that there is no influence of outside boundaries on the dynamics. And boundary conditions set by the initial conditions, it means that essentially, whatever lattice we prescribed in the plane normal to the acceleration, it imposes certain characteristic, certain requirements. I should mention that these conditions, set by initial conditions, they play important role in the linear and nonlinear regime, but then they can be disregarded in the mixing regime. So how the problem has been treated as soon as it's so complicated? One of my students once mentioned that complexity has a tendency to self-regularize. And based on that, actually, even though, I started to work on this group theory approach much earlier than I heard that message from the student, but I would like to mention that the approach that we have been applying uniformly through this problem is based on group theory. So what is a group? Group is an algebraic structure. Roughly speaking, it's in simple words speaking, it's a set of elements. If you have some elements A and B which belong to the group, then their product, binary operation, which is called product, also belong to the group. Furthermore, this product has a property of associativity, and there is a unit element in the group. And for each element of the group, there is an inverse element, such that the product of element and inverse element belong to the group. What is important? Why do we use this group? Because the group itself, as an algebraic structure, it does not exclude. It keeps everything in. So whatever, symmetries we would like to impose, it will be keeping them in. It does not exclude. The group theory consideration or group theory results, would it be, for instance, phase transitions, or would it be fluid dynamics? They usually give us more answers than than many other approaches, because it tries to account for all possible symmetries in their representations. And in our case, we have been applying group theory to study scale-dependent dynamics. And in this case, for instance, we were looking for an effect of initial perturbation, whether the initial perturbation in the plane normal to acceleration will have, for instance, a square symmetry. And there is a name for this group, where P stands for periodicity in one or two directions, 4 stands for the fold axis of rotation, and 2 mirror planes are noted by the letters M and M. There is, also the hexagonal group, and there are many other of these groups. In general, there are 7 one-dimensional, 17 two-dimensional, and 235 three-dimensional groups, which people actually who study condensed matter or solid states, they know very well. We consider only two-dimensional groups or one-dimensional groups, because for our purposes, this suffices. So in the scale-dependent regime, we actually have this symmetry, which is implemented by this symmetry set by the initial conditions, whereas in the scale-dependent self-similar regime, we also may realize the scaling transformations. So in order for us to see, let me just briefly outline the methodology, and I will go very quickly, because if it's too mathematical, please forgive me, but sometimes we just need to proceed through the sense. First thing would be for us to derive the structure of the flow fields. And would it be compressible or incompressible flow? We may show rigorously that in general, in this case, in the bulk, we would expect the vortex-free, essentially potential motion in the bulk. Would it be compressible limit or an incompressible limit? So this would allow us, especially in the large scales, to presume that the flow field might be represented as a gradient of the potential. And then we will solve for the vector, which is represented by the potential of the heavy and light fluid, as well as the interface perturbation. We solve the boundary value problem. We do it by using irreducible representation of the group for the fields applying some global expansion. For instance, for the Fourier series that has a hexagonal symmetry, which is marked by the letter 6 here, we will have an expansion like this for the heavy fluid, and somewhat similar expansion for the light fluid. We also will use the local expansion in the vicinity of a regular point, for instance, tip of the bubble and spike. What is after we will do this sense, we substitute all these structures into the governing equation, we re-expand them, and we define the characteristic movements, which are actually the weighted functions of the Fourier amplitude. In other words, in this description, when I derive the system, even though this is just term M1, but there is an infinite series of Fourier harmonics behind each term. We can do it in the first approximation, we can do it in the second approximation, we can calculate it in any approximation, which allow us to find solutions, to study their convergence, and to study their stability. Towards this representation, rigorous enough, it allows us to truncate the system in the way we want, in the end, not the very beginning. So we would like to test, whether our choices are correct. Then we will find solution in the early time, late time, and investigate the convergence instability. For instance, if we have a variable acceleration, then we might have essentially two subregimes. In one subregime, we will have acceleration being setting the fastest process, and this is how the solution looks like, where I here is a modified Bessel function. Whereas in another subregime, when the acceleration exponent is smaller than -2, we will have logarithmic growth even in the linear regime of the amplitude perturbation. That is actually also depends on the two integration constants. Now, if we would like to proceed to the nonlinear regime, we will easily find that there is not a single solution, as people traditionally believe, but there is an entire family of solutions. And this family of solutions is, in fact, even though it sounds a little bit artificially, but it does associate it with the presence of the interfacial shear and the drop of the enthalpy at the boundary, at the interface. This is the boundary conditions that should be set here. And what we have here, so depending on what would be the interface malporology or our function zeta, we will have a different shear. We may use actually velocity being function of the, for instance, for bubble as a function of zeta, as a function of interface morphology zeta. Or we may, for instance, scale the velocity as a function of the typical characteristic shear that we might have at the interface in case of Rayleigh-Taylor, which are top two slides, as well as in the case of Richtmeier-Meshkov. And this is both done in hexagonal symmetry, like in a particular case for typical values of the acceleration exponent, and for some specific output numbers. What we see here, that velocity, when we start, our bubble becomes more curved, velocity start to grow. So it was actually a planar bubble here, then the bubble start to grow, then it achieves maximum velocity. However, when the bubble becomes very sharp, essentially approaching the maximum of the shear, the velocity decays. And the reason is that in this case, when we have a very strong shear at the interface, theoretically, the large shear is capable to maintain the pressure on its own on the interface. It's a sort of a stagnation point. So the largest shear is not necessarily the possible, the largest shear corresponds to the possible curved bubble, but it's not necessarily the fastest velocity. Now, what is important here, and I will be emphasizing this now throughout actually the text, RT dynamics is essentially interfacial. We have potential motion in the bulk, we have potential motion in the other bulk, we have vertical structures produced by the interfacial shear at the interface. However, what we have here is that there is intense motion in the vicinity of the interface, and there is effectively no motion far away from the interface. And it's actually a characteristic feature of the dynamics. In high energy density environments, usually RT dynamics is set by variable strong shocks. And in this case, our dynamics is a superposition of two motions. It's a background motion of the fluid bulk and the growth of the interface perturbation. So this is actually for three-dimensional bubble. This is for three-dimensional spike. Let me actually illustrate it here. So what is this? It's a strong shock-driven RM dynamics. In Richtmeier-Meshkov, in Rayleigh-Taylor, it will be actually somewhat similar. So what we have a light fluid and heavy fluid, and shock propagates from the light to heavy. Then it pushes the system to develop. And what we see is that there is a growth of the interface perturbation, and we observe this growth here. But also there is a motion that's like, the entire structure, including the fluid between the transmitted shock and reflected shock, as well as the interface as a whole, they move as a whole with a certain background motion velocity. What is important here is that, that this background motion and interfacial growth, they're quite different processes in terms of capturing the scales, because the background motion, it occurs even for a planar interface, and it can be supersonic or even hypersonic for strong shocks, hypersonic or hypersonic, very large. Right? Whereas interfacial growth, it occurs only when we have a perturbed interface or perturbed flow of fields, and it essentially is subsonic and, in fact, nearly incompressible. So in a sense, what our dynamics is, it's like, the thing moves hugely at a huge velocity, like, maybe like in a train with a supersonic speed. However, the processes that occur there at the interface, they're very, very slow compared to this background motion velocity. And for an estimate, we may presume that our background motion velocity is approximately 10% of the shock velocity. The initial growth rate is about 10% of the background motion velocity. The nonlinear mixing is smaller than 10% of the initial growth rate, which give us actually the requirement for the numerical code accuracy. In order for us to capture such things carefully, we need to calculate to ensure that our accuracy should be 10 to the minus 4, 10 to the minus 5, or even higher. It's a killing factor for any numerical simulations. And somehow, for a particle methods, these sort of dramatic processes, they might be easier to measure models than for CFD methods. This is actually figure also illustrates us how the instability may progress with time from some initial moment to some later on nonlinear regime, and it also illustrates how our initial growth rate depends on the initial amplitude. And what we see here is that there is indeed, when the amplitude starts to grow, it grows linearly, but then there is a saturation and then there is a decay. And there were many groups of people who were actually trying to model this decay as a power law function. We believe that it's actually stronger than that. We believe that actually it is an exponential. And I don't present the experimental picture, but it does. Within 3 significant digits, it agrees with experiments pretty well. And I can show actually the reference on the results. What is important? Would it be structure-driven flow, or would it be just our classical Rayleigh-Taylor? The dynamics, the velocity field in Rayleigh-Taylor and Richtmeier-Meshkov instability remains interfacial. This is the direct numerical simulations by the diffuser interface and volume fluid method. The paper has been just accepted in the physics of fluids, as well as smooth particle hydrodynamic simulations. If it would be strong shock-driven regime, they reconfirm the result, the conclusions of the field theory, of the group theory approach. And what we see here is that indeed there is very intense motion in the vicinity of the interface, and there is effectively no motion far away from the interface. Compared to the series, there is a distinction, which is actually tell us why the viscosity is a critical factor to account for. Because in the series, the maximum of the velocity is achieved exactly at the interface. But when we look at the simulation, we see that the maximum of the velocity achieved a little bit below the interface, essentially probably because of the appearance of some viscous layers that actually exist in this, because of the numerical or because of the realistic physical viscosity. So now, from this, abstract structures and group theory, let's proceed to something more, maybe physical. So consider a parcel of fluid in a flow, just from some general consideration. And I would like to point attention that even though what I will be referring to might sound similar to you, because people were first putting these arguments forward in the buoyancy drag models, we proceed from somewhat different perspective, and we can obtain the group C, the buoyancy drag model results in a certain approximation. We can rederive them in a sense, even though I'm not sure whether they can rederive our results. So if I consider a parcel of fluid somewhere here in the flow, then its dynamic is driven. We have a situation, the momentum of this parcel of fluid is being gained due to buoyancy and being lost due to dissipation. So the rate of change of momentum is force, the rate of change of energy is power, or force times velocity. The rate of momentum gain is a buoyant force, it's the rate of energy gain divided by velocity, and the rate of momentum loss is a dissipation rho loss, or a rate of energy dissipation divided by velocity. Now, rather than having these huge equations, with whatever absolutely huge boundary conditions, we rather write a system of differential equations. And I would like to point your attention that we have a specific balance. So the balance is counted per unit mass, not per unit volume. In other words, this description precludes appearance of such things as an added mass coefficient. There is no added mass coefficient here, and inertial term is always 1. Why do we have a specific balance or a balance per unit mass? Because in our boundary conditions at the beginning, we had a boundary condition, the continuity of normal component of velocity, that is independent of the density ratio. So it tells us that the system does not care much about density itself. It cares about how the balance is being kept per unit mass. So mu tilde here is the rate of momentum gain, and it is associated with the rate of energy gain epsilon tilde, which is actually velocity times some buoyancy term times acceleration. It's a buoyant force. And the rate of momentum loss is an energy dissipation rate, or epsilon divided by velocity. We may call it sort of a dissipation force. The rate of energy dissipation is a CV cube divided by the length scale. And this is true in Kolmogorov, but essentially it's just a the characteristic length scale it's not necessarily should be the Kolmogorov turbulence. What is important here is that in this consideration we actually link the rates of energy dissipation and rate of momentum loss in one consideration and also connected to the dynamic. So power force are related like that. So what is important that momentum model has the same symmetry as the conservation laws, and what is even more important that we may directly derive these parameters B and C, which are free parameters, from the governing equations. Particularly, What is interesting that our parameters B and C are different in the different regimes. So what happens in the linear regime is not the same buoyancy in the nonlinear regime, and is not the same buoyancy in the mixing regime. Similarly, the drag parameter, they are different for the bubbles and for the spikes, and they are different for the in the linear regime, nonlinear, and mixing regime. They are more complicated than some particular functions depending on the output number. In the linear regime, the buoyancy parameter grows linearly with an amplitude or with a characteristic curvature, whereas the drag parameter is a constant value dependent on the output number. In the nonlinear regime, buoyancy parameter depends on the density ratio or the output number and interface morphology, and same is true for the drag parameter, and n stands here for the linear. Whereas in the mixing regime, our buoyancy and drag parameters may be free parameters, and they also may be independent stochastic processes due to the multiple scale contributing. So we can directly link the two group theorem implementations, in a sense showing how to derive exactly the buoyancy parameter for the bubbles, which on the left, and for the spikes, which on the right, as well as the drag parameter for the bubbles on the left and for the spikes on the right. And these are all analytical expressions, so there is no numerical numbers here. So what is clearly here is that our buoyancy, and this buoyancy, first of all, for bubbles is greater than for the spikes. Please notice that the same functions of the density ratio, and the same is related to the bubbles, to the drag, because the drag and buoyancy for the bubbles, they are overall greater than for the spikes. If we will be just considering Rayleigh-Taylor solution or a Richtmeier-Meshkov solution as a as a solution of our ordinary differential equation, we exactly will be able to reproduce the solutions we have been obtaining before within the framework of dynamical systems. So this is how our bubble behave, and they are all scaled with the fastest bubble velocity. And this is how our spikes behave, and we see that the spike actually becomes singular when output number approaches 1. So in fact, it's interesting that actually for the spike behavior here, we will have a situation that when our output number becomes smaller, the region of validity actually converges to the point when output number becomes, so we have actually a limit of 2 to fluids with equal densities, then we have probably the broadest interval here. What is interesting is that in Richtmeier-Meshkov, even though we have exactly the same coefficients, we have completely different behavior, particularly for the bubble. The smallest drag, in this case, buoyancy does not play a role, only drag coefficient, drag parameter matters. So the smallest drag is achieved for the flat bubble, and the flattening of the bubble front is observed in all experiments and simulations. Even people sometimes don't even notice it, but it's actually clearly seen from the pictures. Whereas for the spike, we have a similar behavior, essentially such that the fastest spike in Richtmeier-Meshkov is the same as the fastest spike in Rayleigh-Taylor case. And this is, again, all analytical solutions. One more thing that I would like to emphasize about the buoyancy and the drag is essentially velocity scaled, with the fastest velocity, and the buoyancy parameter scaled with the largest drag. And this is for Rayleigh-Taylor bubble. And you see, how non-trivial the behavior, the dependence of the velocity in general on the buoyancy parameter. This actually, how to say it, to my eye, theoretical eye, that plot looks so nicely that it cannot be wrong in general. So because it's a nice loop, in fact, here. For the if velocity versus drag, it would be somewhat different behavior, and we see how we may progress from various solutions. In fact, there are a number of special solutions here, and I marked them the outward bubble or outward spike. These are solutions that correspond to the fastest possible bubble or spike. Laser drag bubble or a laser drag spike that use the same velocity dependence as in has been traditionally presumed. So it would be 2a divided by 1 plus minus a. Taylor bubble or Taylor spike with a constant curvature. Critical bubble or critical spike, it's the largest possible curvature. And flat bubble and the flat spike, which are noted here. What is important that for these three solutions, like outward bubble, laser drag, and Taylor parameters, actually, would it be bubbles or spike, we actually would be pretty close to traditional models, which is actually such as a buoyancy. They will not be exact like that, but they would be very close. In some output numbers, they would be the same. For some output numbers, they would be departing within 15 to 20%. However, what is the special thing, that any of the special solution has an interfacial character of the dynamics, which is probably in other models or in other approaches has not been emphasized. So now, I think since we have a pretty good understanding, actually there is actually one more thing to which I would like to point your attention, which is actually here. So in fact, for the spike, we always have a solution with a zero drag. at a finite curvature. Always there is a solution with a zero drag at a finite curvature. What it tells us that the bubble, the spike, may start to accelerate without actually being processing through the merger process. And we call this transition to mixing without merger process being going through the amplitude dominance mechanism. Because in this case, the amplitude become a characteristic length scale of the process, and as a result, the effective drag force decays, and as a result, the flow starts to accelerate. So in fact, we do not need to have a mixing, we do not need to have a bubble emerge in order to, or a spike merge in order to generate, to produce to the mixing. Now let us consider the self-similar mixing and its connection to self-similar turbulence. For many years, maybe starting from the mid of 60s, especially in a particular example of Rayleigh-Taylor with the mixing with a constant acceleration, it was considered as a Rayleigh-Taylor flow as a sample case of a super turbulence. Why it would be so? Because its velocity scale increases with time, its integral scale increases with time. As a result, its Reynolds number increases cubic with time. It's a very fast increase. Actually, it makes the hurt, I believe, of every experimentalist, to beat, really strongly. The rate of energy dissipation also increases. The formal viscous scale starts to decrease, and the span of scale increases faster than quadratic. In principle, these are parameters that are required for a canonical turbulence to occur. So a lot of results, a lot of efforts have been made to model turbulence effect, presuming that it may develop on Rayleigh-Taylor mixing, and there were a lot of works actually discussing these approaches. So the question is, may Rayleigh-Taylor mixing with constant acceleration be a super turbulence? There were actually a number of experiments which actually were sort of providing somewhat different observations, and I would like to emphasize the experiments of Harry Robbie and also Carolyn Currans and actually other colleagues who actually worked in particularly Lawrence Livermore National Lab. What we see here is that when the Reynolds number can be pretty high, actually exceeding about or exceeding 1 million, the flow still keeps the memory of the initial conditions, and this is actually the finger that protrude from the initial perturbation imposed here. In fluids, it was experiments, even though the acceleration were not as high as in high energy density plasmas, but it was actually orders of magnitude smaller, but the duration of experiment was longer. As a result, it allowed actually to proceed to maybe somewhat higher Reynolds numbers. And as a result, in this case, we also has been observed that even in the very developed mixing regime, there is an interfaciality of the dynamics. So we still have a structure in the essentially in the self-similar mixing regime. So group theory analysis, it shows that in case of constant acceleration, RT mixing may exhibit order. It has strong correlations with fluctuations in steeper spectra, and it differs from Kolmogorov turbulence. So now I would like to proceed to variable acceleration case and discuss a special class of self-similar dynamics. So when we have our asymptotic solutions like this, we can derive our solution in the Rayleigh-Taylor sort of regime and also in the Richtmeier-Meshkov sort of regime. And when we talk about Rayleigh-Taylor type of dynamics, it's a dynamic driven by acceleration. When I'm talking about Richtmeier-Meshkov type of dynamics, I presume that this is dynamic driven by some deterministic conditions. Specifically, if there is a characteristic length scale, which I determine as a H naught, and characteristic velocity scale, or characteristic shear, which I define with a V naught, then we actually can build a typical acceleration, critical acceleration, that will be defined by these parameters, whereas the critical exponent here is set solely by the flow drag in the mixing regime. So what is interesting is that when we start to decrease our acceleration exponent from positive infinity, we first have the flow that is being accelerated. At a equal to -1, we have a stagnant, steady moving flow. Below 1 and negative greater than a critical, we have a flow that is actually being decelerated. And we have RM mixing when we have actually our exponent smaller than critical. The presence of this critical exponent is seen in the dependence of the prefactor in the solution, because we see that the closer our exponent is to the critical exponent, the larger this prefactor becomes. It actually is indicative that our transition from RT mixing to RM mixing is critical in nature. And why is it a singular in nature? Why is it a singular in nature? Because there are two different set of dimensional parameters responsible for each of the process. In Rayleigh-Taylor, we have acceleration strength being the primary dimensional parameter responsible for the entire process, whereas in Richtmeier-Meshkov mixing, we have a sort of artificial, but it's not artificial, it's a G-critical parameter which is set by deterministic conditions. And what we see that in our RT regime, RT mixing is driven by acceleration. Its exponent set by acceleration. Its prefactor depends on acceleration parameters on the drug. Whereas in RM mixing, the flow is driven by some initial growth rate. Its exponent set by the drug. Its exponent is independent of acceleration parameters. And prefactor is set by deterministic some initial conditions. What is remarkably, that even though acceleration effects are present, they are non-important. Because RM mixing, even though it's driven by some initial growth rate, it moves quicker than acceleration prescribes. And RT to RM transition is singular in nature. So this is actually an illustration. It's a stochastic code that has been applied to model RT mixing and RM mixing with a drug parameter being some stochastic process. And what we see here is that above critical, this is G, which is my acceleration, and this is V dot, which is the system acceleration. We see that they're parallel to one another, indicating that acceleration actually drives the dynamics. Whereas in this regime, in RM mixing regime, which is below the critical, we have our G, which is here, it's a log-log scale, and we have our V dot, which is given here, and we see that actually the acceleration quantitatively does not matter, even though it's present, because there is some initial growth rate that drives the flow. About RT-RM mixing versus Kolmogorov turbulence, just would like to give you some illustration from the fluid dynamics point of view. This is isotropic homogeneous turbulence, and this is anisotropic Rayleigh-Taylor mixing, according to people who were studying and investigating the system and fluids for a long time. Now, let me actually go very quickly, maybe through the scale invariant turbulence. Maybe I will proceed, better proceed to the scale invariant Rayleigh-Taylor mixing from the group theory perspective. What we have our conservation laws. I'm returning back to them. We have also the viscous scale. We have plus boundary conditions, plus initial conditions, etc. So the process itself has a number of symmetries in statistical sense. This dynamic is non-inertial, so no Galilean transformations. It has translations, rotations, and reflections in place, and it also has a scaling invariance, meaning that if we increase characteristic length scale, time scale, velocity scale, conditional that viscosity is scaled like that, and acceleration scale, strength is scaled like that, we will have that our scaling exponent in this case should depend on the acceleration exponent. And the characteristic invariant of this value, we call it a modified rate of change of specific momentum. It actually may be viewed as an eighth order derivative of the rate of momentum loss, and may be calculated actually rigorously from the characteristics of the flow. If I would like to scale it with the velocity and length scale, this would be the characteristic scaling. I would like to mention that similar discussions when we apply it in Kolmogorov turbulence, we have a different invariant value, and this is the rate of energy dissipation of specific kinetic energy, which is actually becomes the important scale. Invariant value. For self-similar turbulence, we have an energy dissipation rate being a scale, an invariant form, meaning that if we will measure this value at large scale or at small scale, it will be the same constant, maybe with some error bar, but still the same constant. And this is for the exponent one sort. Whereas for self-similar mixing, the measure of scaling invariant is modified rate of momentum, which is here. And the scaling exponent is presented here. Whereas for Richtmeier-Meshkov mixing, we have a critical exponent that is represented here. So we see that RT and RM mixing and canonical turbulence, they have different scaling properties. If I will be accounting for the same features, for instance, for the Reynolds number scaling, in Kolmogorov turbulence, we have, because of the invariance of the energy dissipation rate, we have a Reynolds number scaling with a power 4 sort here, whereas in Rayleigh-Taylor mixing with a variable acceleration, we have this type of scaling. Similarly, for the viscous scale, we have this expression in Kolmogorov turbulence, and for the viscous scale with variable acceleration, we have this expression for which depends on the acceleration strength as well as on the characteristic viscosity. And I would like to point your attention that this viscous scale, which we are looking in the deeply nonlinear mixing regime, is the same, is comparable to the mode of fastest growth that we may evaluate in the linear stage of the instability development. So the system does keep a memory of what has been happening in the very beginning, so it doesn't become any smaller. And definitely we may evaluate the span of scales. If we will be looking at the spectral properties, then for kinetic energy, for instance, for one of the velocity components, we will have a classical -5 sort Kolmogorov spectra based on the invariance of the energy dissipation rate, so it's our dimensional parameter. Whereas for RT mixing, we will have a different scaling dependence with a different actual values of the exponent. And we can find that depending on the acceleration exponent, A, it may be steeper than Kolmogorov spectra, it may be the same as Kolmogorov spectra, and it may be more gradual than Kolmogorov spectra. So it might vary. Would it be more steeper or more gradual? However, if you will be looking at the spectral of the density, in all of the cases, would it be Kolmogorov turbulence, Rayleigh-Taylor mixing, or Richtmeier-Meshkov mixing, we expect the same spectral exponent -1 for the density fluctuations, as well as for all possible higher order moments of the density fluctuations, for one important reason. All these properties are specific. So in Kolmogorov turbulence, it's constant density, so all the balances are counted per unit mass. Density does not play a role. In Rayleigh-Taylor mixing and in Richtmeier-Meshkov mixing, despite we have a density gradient that was essentially the reason for the instability to develop, it actually, the dynamics is counted as a balance per unit mass, not per unit volume. And this is actually an important thing to verify in the, for instance, in numerical simulations or in the experiment, and this is confirmed by the experiments and simulations. Now, I would like to point your attention also maybe to with a few important remarks here before I proceed to comparison with experiments and simulations, that we have a interesting situation here. Kolmogorov turbulence is a stochastic process. It fully blackens out any memory of deterministic conditions. And the reason for that is that, for instance, if we consider two parcels of fluid which are entrained into a motion in a turbulent flow, like with a characteristic time delay tau, then the relative velocity would be much smaller than the turbulent velocity fluctuations. And the ratio of these fluctuations to the mean velocity will become a constant value. So in a sense, turbulence is a process of taking energy from an external source and pushing it toward fluctuations. And these fluctuations are stronger than any memory of deterministic conditions possibly be. Whereas in Rayleigh-Taylor, it's a different situation. We have actually the relative velocity of the two fluid parcels would be same order as the process fluctuations. And furthermore, their contribution to the mean, their value compared to the mean velocity would be actually a function of time, maybe increasing with time or decreasing with time. So in a sense, in Kolmogorov turbulence, fluctuations are self-generated and deterministic conditions do not play a role. In that sense, the turbulent fluctuations are much stronger than any possible deterministic conditions. Whereas in Rayleigh-Taylor mixing, fluctuations are set by deterministic conditions. And the smaller the acceleration exponent is, the closer the flow is to Richtmeier-Meshkov flow, the stronger the effect of deterministic conditions will be. This is picture, it represents a scaling exponents, scaling exponent values for the velocity scaling, for the Reynolds number scaling, and for the energy energy density in the spectra. So what we see here, when our acceleration exponent is very large, right, we have a motion that is actually superballistic. When our acceleration exponent is 0, we have actually motion that is fully determined by the gravity acceleration, it becomes a ballistic. When our acceleration exponent is -12, we have a process that is quasi-Kolmogorov, in that sense that all the characteristic scaling laws, they would be the same, but there would be the word quasi there, and the reason is that in Kolmogorov turbulence we have stochastic process, whereas in RT mixing we have a deterministic process. If we will go even a little bit below, we have actually a point at which would be a sort of a steady flex point, so above which the larger velocity corresponds to larger scales, below which larger velocity corresponds to smaller scales. And if we would proceed to Richtmeier-Meshkov regime, which is here, we actually might expect positive values of the exponent of the spectral density. And the meaning of this actually positive value of the exponent, which I would like to illustrate here, is that as soon as we below -1 of the acceleration exponent in this subregime, the larger the length scale, the smaller the velocity. Whereas in turbulence and everywhere above -1, the larger the length scale, the larger the velocity. So when we have a flow that is being increasing with time, or even if it would be decreasing with time but not very strongly, we still might expect the situation that larger velocities will be exhibited at larger length scales. However, in Richtmeier-Meshkov sort of limiting case, the larger velocities will be corresponding to the smaller scales. The process become even like, quasi-diffusive or even subdiffusive. And in order for us to have a better picture, we may take a, tea bag, put it in a cup, and see, like, in a diffusion, right? We have a coloring in the vicinity of the bag first, and only then it starts to approach the sides of the cup, which is actually the characteristic process. So it's actually quite interesting how the molecular processes or processes like that might be associated with the fluid velocities. About sensitivity to initial conditions, this figure actually illustrates us when we have a Richtmeier-Meshkov flow, it's a smooth particle hydrodynamic simulations with exactly same initial conditions. So flow conditions are the same, Mach number is 5. Output numbers are the same, like for instance, here it's a 0.6 and here it's a 0.9 in these two pictures. Initial perturbation wavelengths are the same, and the ratio of the initial perturbations, like, the same. The only difference between figures on the left and on the right is the relative phase of the initial perturbation waves. We had two waves which are in anti-phase configuration on the left, and they create an ordered structure later on when we sit in the deeply nonlinear regime. And in this case, on the figures on the right, we have two waves which are at random phase, essentially it's a phi equal to pi over 2, and they create disordered process, and some may even call it turbulent, but in fact, actually, it's a deterministic process because its noisiness is fully set by the deterministic conditions. In terms of supernova remnants, it's actually an important application of our theory is actually quite consistent and explains the observations because, in fact, actually here it has been found in supernova remnants that filaments that are produced by the Rayleigh-Taylor or Richtmeier sort of type of structures, they move at a speed higher than a blast wave may prescribe. And this is fully consistent with our theoretical analysis because if I will be going back here, like, to this figure, where the blast wave sits, they sit in the interval from -1 to -2, everywhere here. So what has happened in this regime? If we start our flow, it will be Rayleigh-Taylor, driven by acceleration in the linear regime. It will be Rayleigh-Taylor, driven by acceleration in the nonlinear regime. But it will become Richtmeier-Meshkov, driven by some deterministic conditions in the mixing regime. So, and as a result, the flow will be moving faster than acceleration prescribes. Because this process is essentially a subdiffusive process, it will have a different mechanism for energy transfer and localization at small scales. Because in a subdiffusive process, the process is so small, so slow, that if an energy pocket is created at some small scales, it will be just sitting there and not steered with an ambient flow. Now, also, in Richtmeier-Meshkov cases, this is actually an illustration how the hot spots may be produced because our entire system, as we were discussing before, it moves at a huge velocity, might be hypersonic velocity, but the interfacial flow, actually, the interfacial structure moves very, very slowly, nearly incompressibly. It creates a situation when the bulk starts to adjust to the interface, producing a lot of small structures in the bulk. And what we see here, this is actually cumulative jets that may be extremely hot. Actually, their temperature are twofold of that of the ambient. And this actually may be the places where, for instance, in a supernova environment, some reactions may be initiated. I would like to say that our theory achieves a good reasonable agreement with the data and experiments at plasma at the Omega facility, which are on the top, as well as in the National Ignition facility, which is here in the low drive case. So in this case, we are able, actually, furthermore, we are able to explain the difference in the interface morphology that has been observed in these very important experiments at the National Ignition facility, where in the low drive case, low flux case, there were a lot of observation of a lot of more visible interfacial structures, where in the high flux case, we had actually nearly shear free dynamics. Actually, on the talk on Monday, I was trying to explain that if we have some fluxes, significant fluxes of mass and heat across the interface, it would immediately lead to shear free dynamics. So actually, there is no shear at the interface. And this actually explains qualitatively why we may not have shear here. Whereas the intense interfacial structures here, they explained by the fact that we have actually acceleration that is very close to the 0.2 to -1. In fact, at this situation, we will have the velocities that will be faster at smaller scales rather than at larger scales, creating a more visible structure. I will give, maybe a few more examples very, very quickly. So some future experiments for the NIF can be proposed with a variable acceleration, and this is actually the series simulations and prior NIF experiments agree with one another. And this is our numerical simulation by diffuse interface and volume of fluid methods, showing actually the experimental point presented here. What we see in the simulations that RT growth strongly depend on the acceleration, and this difference is large enough to be confidently detected in the NIF experiments, showing, for instance, how the amplitude would change with time, or how the characteristic time, what would be the characteristic time for the same values of the amplitude for acceleration that is increasing with time, that is constant, and that is decreasing with time. If I would like to proceed with experiments in fluids, I just would like to illustrate maybe the concept of the similarity. This is a situation when we might impose some initial perturbations that would be actually growing self-similarly with time, not necessarily turbulent. But more important, if I would have a minute maybe or two, I will just very quickly illustrate the spectra, because we don't have much spectra in plasmas, unfortunately. I mean, we do have actually, we did compare with the spectra at the, which have been taken at the Sakla facility, and we obtained very similar results. But this is actually the spectra and experiments in 2017 Akula Ranjan paper. Actually, this is the experimental facility initially built by Malcolm Andrews. So these are velocity fluctuations, these are density fluctuations. And we found that the best fitting function, which would be spanning substantial dynamic range, essentially from 80 to 400, this would be the function that will have a characteristic alpha close. It will be compound function, which is a product of power law and exponential function, such that our exponent of the power law is close to -1, and this would be our beta for the exponential decay rate. If we will be looking for the density fluctuations, we will have a completely different situation. We will have that our alpha is not close to -2, is close to -1 as prescribed by our theory, and this is a reflection of the fact that we have a specific dynamics. And it's interesting that our beta here and here is different threefold. And the reason why it's different threefold is actually has a simple physics explanation, because here the flow is actually maybe still keeping self-similar behavior for velocity spectra, but it still will be multi-phase in terms of the density fluctuation. So it does keep the memory of deterministic conditions. The data fit method, it was described like, it was like, we actually did not restrict it in any way. We considered it like, solving optimization problem and investigating what would be the best possible interval to ensure that we will have the smallest possible errors for the parameters of the fitting function, as well as a high enough goodness of fit. In other words, we analyzed residuals, which experimentalists and numerical people often don't do because it's an extremely boring technique, but we have done it. So, and I personally admire of my colleagues of David Pfefferly and Kurt Williams who did this work. And this is a very famous paper, right, which shows actually Cabot and Cook numerical simulations in back in Nature 2006. Somehow I lost my point. They are usually interpreted as a -5 sort spectra. But what we see from here is that with very high statistical confidence, essentially R factor is 0.99, in a very broad interval from 20 to 1200, essentially, we may approximate the spectra through the, and this is actually clearly seen that there is indeed an exponential path if you will present the spectra in a log linear rather than log-log scale. And what we see here is that the exponent of the power law is quite close to -2, whereas explode for the velocity fluctuations, for the density fluctuations is close to -1. But there is one distinction between the experiments. In experiments, the beta for density was quite different, threefold, for those for the velocity, whereas here there is the same value. Probably this may be as a result of the numerical modeling technique, which was actually the large HEDS simulations. For the future experiments, I probably will not be discussing it because it's still in fluids. And I would like just to mention very briefly that in general, even though I spend a lot of time trying to prove that, not trying to prove, but proving and convincing you that Rayleigh-Taylor dynamics and Richtmeier-Meshkov dynamics, even though they're self-similar, they have completely different properties in Kolmogorov spectra, this analysis is actually fully consistent with the classical approaches. And for instance, we may, for the spectral density, with account for invariant form, which is rate of momentum loss for the constant acceleration, we may exactly obtain from the Kolmogorov spectra our k to the -2 spectra and vice versa. Because if we will be accounting for the sense accurately with just considering what is the control dimensional parameter of the process. In Kolmogorov turbulence, it's a power of external motor that supplies energy to the system at a constant rate per unit time, per unit mass. In Rayleigh-Taylor, this is the acceleration strength, which also supplies energy in a sense, source of energy, and also of momentum. And I would like to proceed to conclusion. So our theory applies group theory to study non-equilibrium dynamics of interfaces and mixing, finds invariance Helin spectra of Rayleigh-Taylor, Richtmeier-Meshkov dynamics. We see that it's a quite different processes compared to canonical Kolmogorov turbulence, also quite different processes compared to blast waves. But what is good is that even though we started from some abstract algebraic structures, such as group theory, we are able actually to come to a clear physics picture. And I would like to point your attention that within this approach, because group theory is broad enough, it does not miss anything, we are able to derive in certain limiting cases the results of most of the existing models, whereas like as a particular limiting case. So for me, which is actually, I also believe may be good because, like, if people apply these models for calibration of their data, It means that, if those models were consistent with the data, we're also consistent with the data, even if you don't compare, a specific direct comparison. But we would like actually to emphasize the need in a extensive data analysis, and we are happy to help because we do have, expertise in various approaches. So thank you so much for your kind attention and for your valuable time.
Thank you very much. We already have a couple of questions online. There's one from Nathaniel Roth. Can the theory presented here be used to develop alternative mixing models and hydrodynamics codes to RAND's models?
Yes, exactly. Absolutely. Because if you are talking about, myself, I don't do it. I don't develop numerical codes, so I cannot tell you what the particular algorithm will be. But definitely there are the certain diagnostic parameters which we need to account for. Specifically, we need to keep in mind that if it's a constant acceleration, it should be the rate of momentum loss that is being an invariant quantity rather than energy dissipation rate. As a result, it imposes a lot of limitations on what the particular properties, spectral properties of all the quantities in the flow will be, and we may not expect them to be the same as in Kolmogorov turbulence.
Thank you. And there's a question from Tamara Haksamali, who asks, will it make sense to take into consideration the existence of surface tension of the interface before the instability? And if it does, how important its role is, especially in the linear mixing regime?
Surface tension, it does play an important role, and I should say that especially when we talk about the constant acceleration case, it's actually really determinative role. When we come to the variable acceleration case, I think we need to be more considerate because in fact there might be regimes that it may not play such a significant role. But before I will be publishing a paper, I'd better not discuss it because essentially, when the paper is published, you kind of think through all the possible consequences, being very cautious about the words that you are saying. So I don't want to confuse people. But in general, yes, surface tension as an effect is an important effect. However, it's not, it might influence certain processes. It might introduce certain characteristic scales. But if you are sitting above those scales, the process still will be driven by the acceleration. So in a sense, there might be the interval of values where the surface tension will, even though it's present, will play effectively no role.
Okay, thank you. So I think in the interest of time, any questions in the room you can do offline. Otherwise, thank you everybody for attending.
Yeah, thank you so much.
See you next time. Bye-bye.